Hello everyone. In this session, I am going to discuss the concept of recurrence relation, which is widely used in many real life situations, many real life application it is having. Like it is used to model population growth situation. It is used to find the solution of various game theoretical problems. Means what I want to say, like if there is a game and it's satisfying certain condition, that game can be modeled in terms of recurrence relation, and the solution of this recurrence relation will give you the solution of that game too. It also is used in financial mathematics to find growth or decay curve related to your investment in terms of arithmetic or geometric progressions. Okay, so these are the few applications related to the recurrence relation. Now come back to back to the original definition, or what exactly it looks like in terms of mathematical definition. So there is a one thing which is called as a sequence, and I hope everyone is aware about the sequence. So a sequence is what? Sequence is what? A sequence is an arrangement of number which satisfying some particular law. Arrangement of data, or we can say a collection of data, better to say, where the terms follow a definite rule. Means what exactly? That term can be calculated on the basis of the rule that is followed by the previous term. Okay, so a recurrence relation is used to model a sequence in terms of a mathematical expression. Now, there are certain situations where we get a sequence from a real life situation. So, what the total hierarchy is what? We choose a real life situation, like it may be any game, it may be a population growth model, it may be any problem related to financial mathematics. We'll generate a sequence from it, and that sequence can be converted in terms of a recurrence relation, and the solution of this recurrence relation will gives you the solution of that particular problem. Okay, so in short, if I want to give a one-line definition for a recurrence relation, so recurrence relation is a relation which express the terms of a sequence in terms of its previous term. That means whatever term we are talking, it can be expressed in terms of its previous term. Then that expression we called as a recurrence relation. When I'm saying that in terms of previous term, yes, there are few terms which can't be expressed in terms of its previous term, called as the initial term. Like if we do have the first term, it can't be expressed in terms of its previous term because no previous terms occur from this. Okay, this is what exactly we do have when saying that in terms of previous term, it may be we are expressing sequence in terms of one, two, or more than two previous term. Let me take few examples on it by sharing my screen. Okay. So first, the mathematical definition, as I already discussed. So an expression in which every term except few of a sequence can be expressed in terms of the previous term is called as a recurrence relation. Let me write an example so that you get more clarity on it. So suppose that we do have a sequence and its term is written, let it be as 2, then 5, then 8, then 11, then 14. I just take a simple sequence and these are the few of its term, which is 2, 5, 8, 11, and 14. Now over here, I hope everyone is get that how exactly the terms of this sequence are progressing. Like you can see the term is 3 more than the previous term. The term is 3 more than the previous term. Like 5 can be used as a previous term plus 3. 8 can be used as previous term plus 3. 11 can also be used as 8 plus 3. 14 can also be used as 11 plus 3. So the next term over here will be 14 plus 3, that is 17. So over here you can see this arrangement is following a definite rule. So now if I am taking the first term is as A0, like it also depend like author to author. Few take starting term as A0, few take starting term as A1. So do not get confused whether we have started from A0 or A1, both replicate the same sense. So first term if I am taking A0, second term if I am taking A1, the third term if I am taking A2, this term I am taking A3. So this is how the terms of sequence we do have. Now in place of this, the terms can also be written. The first term is A1, the second term is A2, then third term, then fourth term. Over here we call it as zeroth term. Over here we call it as first term. Now I am interested to get a sequence from it. So if I want to write the nth terms of this sequence, can I write it like an equals to an minus 1 plus 3? Yes, so the the nth term is equals to the previous term plus 3. The previous term plus 3. This is what a recurrence relation for this sequence. That means if I put the values of n in this equation, I get that sequence too. Provided like first term can't be expressed in terms of previous term. So I need to specify some initial condition with it. So I can say that A0 is 2. So this complete expression now we call as a recurrence relation, where this is exact the relation and this is the initial condition. Now by using this recurrence relation, I can find all the term. Like suppose that I am interested to find A1. So put n equals to 1. What I get, A1 equals to A0 plus 3. A0 is given as initial condition. So 2 plus 3, that make it as 5. Yes, so A1 is 5. If I want to get A2, put n equals to 2. So over here what I get, A2 equals to A1 then plus 3. I obtained A1 as 5. So 5 plus 3, that is 8. So this is how we are getting the terms of the sequence from this relation. Over here, this is called as a recurrence relation. I hope you understood the concept, what exactly I want to communicate to you. Any sequence is modeled in terms of a relation. That relation we call as a recurrence relation. That relation we call as a recurrence relation. Be careful. It's not that the relation can be of any nature. Any nature means what? It must have the term in terms of previous term. It's not like I am writing a relation which is also replicating the sequence, but not in terms of previous term. But not in terms of previous term. So this is how we can find the sequence. For the same thing, if I want to write something else like an equals to, if I am writing 3n plus 2, and where n comes out from set of positive integers or set of integer, let us take including 0. So integer, not positive, integer only. On positive side, including 0, I am taking this. So if I am putting n equal to 0, what I get A1, which is 2. Yes, that is the same thing. If I am putting n equal to 0, so A0 is 2. If I put n equals to 1, what I get, 3 plus 2, 5. If I put n equals to 2, 3 to 6 plus 8. Now you can see this relation is also replicating the same sequence. But the question is, can I say this is also a recurrence relation? Can I say this is also a recurrence relation? The answer is no. The answer is no. Why the answer is no? Because over here, n is not expressed in terms of its previous term. N is not expressed in terms of previous terms. Okay. So this can be considered as something which satisfy this recurrence relation. We'll talk on later like what is the solution. So over there we will cover that why an equals to 3n plus 1 satisfy this equation, and if something or some value of an which satisfy this equation, we call it as the solution of this recurrence relation. Understood. Let me take one or more example. So this time, suppose a sequence is given as, let us take the sequence as 1, then 2, 3, 5, 8, 13. So I take one more sequence over here and we'll try to get a recurrence relation out of it. So now the first thing, when you get a sequence, you are trying to make a symmetry between the terms, the logic, the rule. So over here, I can say that the first term and second term is same. Third term is 2, which can be, means we say that it is one more than the previous term, or we can say the sum of the last two terms. Now 3, it is the sum of these two terms. Now 5, sum of these two terms. Now 8, sum of these two terms. Now 13, sum of these two terms. So what relation I am getting over here, I can write it as, like, it also depends, we are starting with 0 or 1, that's totally your call. So suppose that I am starting it with 0, so A0, then A1, then A2, and then so on. So what can I say for an? An equals to an minus 1 plus an minus 2. Every term is expressed as a sum of previous two terms except sum. Now if you see, these two terms can't be expressed as a sum of previous two terms. So what can I do for this? Make them as an initial condition. So with the condition that A0 equal to 1 and A1 equals to 1. Now this completely represent the given sequence, and this we called as the recurrence relation for this sequence. The recurrence relation for this sequence. So this is how we get. Now one more thing, should I start putting n equal to 0, n equal to 1, n equal to 2? That is also need to be decided. There is no need to find a0, a1 as it is already given in terms of condition. So we'll start with a2. That means for this, n should start from greater or equal to 2 from the set of integer. So a2, a3, a4 can be obtained from here. This is a very famous sequence called as the Fibonacci sequence. Okay, and this is the recurrence relation representing this sequence. I hope you understand that how we are getting a recurrence relation from any sequence and what exactly it means. Okay, so writing one more, you can try it by yourself. So this time sequence is 1 1, then 2, then 6, then 24, then 120, and then so on. Try to find a recurrence relation for it. You can pause the video and try to write it. The recurrence relation for this sequence comes out as an equals to n into an minus 1. N into an minus 1. So this is how we can make a sequence for it, like a1 will equals to 1 into a0. That means I need to give initial condition as a0. So this is the recurrence relation for this sequence. I hope you understand the concept. In the next session, we'll talk about the solution of the recurrence relation. I also suggest to all of you, try to play a game online. It's a Tower of Hanoi game. Try to model it in terms of recurrence relation and try to find the solution of the recurrence relation, and that solution of recurrence relation also gives you the solution of that Tower of Hanoi game. So that's all from my side. Let us close this session.